So at this point, we've proved a number of generic existence theorems of integrals. Things like, if the integral of f exists and the integral of g exists, then the integral of f plus g also exists. Now, those theorems are certainly very useful, but they don't help us a whole lot in actually computing specific integrals. And so it's worthwhile to take a moment to figure out, well, how do we prove those sorts of concrete formulas that we all learned in Introduction to Calculus, things like the integral of x squared is equal to 1/3 x cubed. So I'm just going to do that very quickly in this video. I'm going to take a equals 1 just to make some of the notation a little bit shorter, but the following argument is going to work more or less the same way when a is a general number. And I'm going to fix some partition. And to make my life easier, I'm going to fix this uniform partition, Pn. And again, the details of the following don't depend too strongly on that, but it certainly makes life a little bit easier to choose a uniform partition. So I'm going to draw my function, and I can draw my upper and lower bound functions as well. So here's my function f of x is equal to x squared, or at least very roughly, on the interval 0, 1. And I'm going to zoom in on one part of the partition, looking at the subinterval from I over n to I plus 1 over n. And it's straightforward to check what the lower and upper bound functions are, since x squared is monotone. So the lower bound function just takes this value, which is I over n squared for the entire interval, and the upper bound function takes the right-hand value here, which is I plus 1 over n squared for the entire interval. So those are my lower and upper bound functions, and those give me lower and upper bounds, which I've written down here, sort of more algebraic notation, and those give me upper and lower bounds for the integrals themselves. So the upper bound function u of fpm is the sum from I equals 0 to n minus 1 of the width of the interval times the function evaluated on the interval, which is I plus 1 over n squared. Similarly, I have a lower bound function, which is exactly the same, but it's the sum from I equals 0 to n minus 1 of the width of the interval times the function evaluated at the interval. Now, some of you may remember, and some of you may not remember, that there's a really nice formula for the sum of squares. I'm not going to rederive the formula, I'm just going to use it here and here to calculate the answers to these sums. So that's not really something we're focusing on this calculus class, but it's also something that is not terribly difficult to do if you haven't seen it before. Okay, so since those formulas exist, I'm just going to use them, and we get these explicit exact formulas for the upper bound function and for the lower bound function. And if I look at those two things themselves, I can see that these are polynomials in n, and the top one, if I take just the leading term, I get an n plus something small times 2n plus something small, so that looks like basically 2n cubed divided by 6n cubed. So that's converting to 1/3 as n goes to infinity. And similarly here, although the small terms change, the leading term is still 2n cubed on top and 6n cubed at the bottom. So again, we go to 1/3. Okay. So since the upper bound and the lower bound function both converge to the same number, then the function x squared is indeed integrable, and the integral from 0 to 1 of x squared is 1/3. Okay. So that's fairly short. Now, of course, I cheated a little bit because I relied on the fact that I knew this formula for sums, but of course that has nothing to do with calculus. That's just how we compute sums, and you sort of have to go through that at some point anyways, if you're going to be computing integrals directly. Now, I will say this isn't the only way that we know how to compute integrals, but it's the only way we know how to compute integrals so far. There's another thing that you could do. So at some point, as you probably all can guess, we're going to get to the fundamental theorem of calculus, which tells us how integrals and derivatives are related to each other. Once we get to the fundamental theorem of calculus, we're going to unlock a fundamentally different way to calculate integrals, which is basically the guess and check method. So in particular, one thing we could do as well, we sort of know what the integral of x squared is, right? We know that it's 1/3 x cubed. And so one thing we could do with the fundamental theorem of calculus is guess what the integral is, and then compute the derivative of that thing and check that the function we get back is the function that we started with. And the fundamental theorem of calculus is going to tell us, well, that's actually a proof of this formula for the integral. Why do I call that a fundamentally different method? Well, the important thing is that when you do this, the only thing you actually have to compute from first principles is a derivative. And computing a derivative from first principles, as you might recall from looking at earlier videos or from your experience, is actually substantially easier than computing integrals. In particular, to calculate this derivative here, you just sort of expand a polynomial. It's quite straightforward. You don't have to, at any point, remember what these formulas for the sums are. All right, thanks very much.